Okay, welcome to lesson 8 entitled Acid-Base Reactions. And in class, we started doing our very first titration. And we looked at a titration of a weak acid, acetic acid, HC2H3O2. And remember, what makes this an acid is the presence of this little proton here, H plus. Hi, proton. That was aqueous, meaning it's dissolved in water, and we reacted that with a base, sodium hydroxide, aqueous, dissolved in water. And what makes this a base is not necessarily the presence of the OH. It's the fact that OH is minus. Remember, Bronsted and Lowry said that an acid is a proton donor and a base is a proton acceptor, meaning anything that is negative. When this reaction happens, the hydrogen is going to go with the hydroxide, and that's going to make liquid water, HOH, or H2O liquid. And it's going to make sodium acetate. Now, because everybody here is +1 and -1, the reaction is nice and balanced. Now, the point of titration, which we learned, is to get this reaction to happen perfectly. We want no excess. Okay? So, in this case, we pick one of these to be the titrant. And that's the thing that is going to go in the burette. So in this case, we pick sodium hydroxide to be the titrant, and we fill it up with some volume of that. And in this case, there was a 0.1 molar solution of sodium hydroxide. Okay? And there's a little stop there. And the unknown solution, the thing that we're trying to standardize, remember standardization is to figure out the molarity, some unknown molarity, we put in this flask. And in this case, we put 50 mils. You can really put, it's up to you, you know. I like to put a small amount, not too small, but I usually don't like to use the whole capacity of the Erlenmeyer flask. Okay. And you also want to put in here a few drops of indicator. In this case, we use phenolphthalein indicator. Now, when this titration happened and the indicator changed color, okay, it turned pink and stayed pink as you consistently swirled this flask. And that's what you're looking for. And that's called the endpoint of the titration. And if this started at 0, most people, it took about 40 milliliters for that to happen. Okay? So to figure out the molarity of your unknown, we use the titration equation, which says that the molarity of this case, the acid, times the volume of the acid equals the molarity of the base times the volume of the base. So when we look at this, we don't know the molarity of the acid. That's what we're looking for. But we know that we had 50 milliliters of the acid. And we do know the molarity of the titrant. You always know the molarity of the titrant. We're trying to figure out or standardize the molarity of the solution of vinegar. We knew that that was 0.1. And the volume is the volume that was used. Now, if this, say, started here at 2, then 40 minus 2 would have been 38. But let's just assume it started at 0. And you figure this out, and it leads you to a molarity of 0.08. So we've officially now standardized the solution. And this is how you do it. So in summary, in titration, the unknown goes in the flask with the indicator, and the known solution goes in the titrant. Okay. We use this equation, MAVA equals MB phoebe, to figure out the molarity of what we're looking for. In this case, it was the acid. Okay. So that's our little review of titration. We're going to do titration probably every single day for a while. But let's go ahead and take some notes on a few different types of acid-base reactions. Now, we looked at one specific traditional type of acid-base reaction, but there's really two that we're going to talk about right now. Types of acid-base reactions. Now remember that Bronsted and Lowry defined an acid as anything that can donate a proton or an H+, but they defined a base as not just hydroxide, but anything that's negative. Okay? So there's two types of acid-base reactions. Number one, there's water formation. So these are reactions where you take one thing and you react it with another thing, and you get another thing plus H2O. Okay? And then there's water plus gas formation. And in this case, you have one thing reacted with another thing, makes something plus H2O liquid and CO2 gas. Okay, so in this case, you made just water. In this case, you made water and carbon dioxide. So let's look at both of these types of reactions and some examples of them. Okay, so let's first take a look at water formation reactions. In a water formation reaction, I have a perfect one here that I wanted to write down. They really follow this format. So let's say we have some Bronsted acid, H. We're going to use X here for anything negative. And this reacts with some Bronsted base. Why don't we just call this YOH? Now notice in this case, you have H and OH. Anytime you have that lineup, it's going to be your traditional simple water formation reaction where you're going to get YX aqueous plus H with the OH. And in this case, we'll call this H2O liquid. But what's really important is understanding what is happening on a particle level. So instead of drawing it this way, we're going to draw these in beakers. And this is what I'm going to be having you guys do in class and on the quiz a lot. So we have these two beakers, and they're going to go and produce one large solution. Okay? Say the volumes are additive. So in this case, the acid is aqueous, and what this means is that it's in its ions. So in this case, we have one H and one X minus. In this case, we have one Y plus and one OH minus. And what's going to happen here, like we saw there, is that the H is going to go with the OH. Okay, and that's going to make liquid water that is not broken up. Notice it's not aqueous. And I'm going to circle that just to show that it's not broken up. And we're going to make Y and X minus, which is aqueous, so it's going to be broken up. Okay. Let me show you a standard example of that, like an actual example. Let's say that we have some reaction, HCl, aqueous, reacts with NaOH, aqueous. Okay. So what's going to happen before is just like we saw, the H is going to go with the OH, and that's going to make H2O liquid. And the Na is going to go with the Cl, and that's going to make NaCl aqueous, dissolved in water. Let's show this on a particle level. H plus and Cl minus in solution because it's aqueous. In the other beaker, we have Na plus and OH minus in solution because it's aqueous. I can see what's going to happen. This plus is going to go with this minus and vice versa. So over here, I'm going to get one new big beaker containing all the products when they are mixed. The Na plus and the Cl minus are going to remain in the ion form, and the H is going to go with the OH to make H2O liquid, and I'm going to circle that to show that it's not broken up. And that's what's happening in solution. Let's look at the next one. The next one we have is the water and gas formation. And now this follows a very, very, very similar format. Okay? Very similar format, but a little bit different. So we have our acid, HX. We know it's a Bronsted acid because it gives H+. But instead of reacting it with YOH, we're going to be reacting it with Y connected to CO3 2-. And because in this case, we're assuming Y is +1, it's going to be Y2CO3. Now I want you to really pay close attention to this H and this CO3 2-. Whenever you have H and CO3 2-, those two immediately break up into water, liquid, and carbon dioxide gas. And what's left over now is that y, which is plus 1, connected to that x, which is minus 1. And in this case, you obviously have to balance this reaction such. Okay. Let's look at what's happening in solution here. Now we have two hx's, so we have h plus x minus, h plus x minus. And that is going to react with this aqueous solution, which has two y's. So y plus, with one CO3, 2 minus. I can see what's going to happen here. Remember, the H's are going to go with the CO3, 2 minus, and that's going to make H2O, liquid. I'm going to circle that, and that's going to make CO2 gas. Now, neither one of these am I going to break apart, but the gas, I'd like you to draw these little bubbles coming off it, just to show that that's going to bubble to the top as a gas. And we're going to be left now with the y pluses and the x minuses in the form of 2yx, but since they're in solution, we're going to show it that way. Let's look at a tangible example of this one. Okay, so a tangible example here would be something like this. HNO3 aqueous plus sodium carbonate. Aqueous. So I know it's an acid-base reaction because I see my acid, and in this case, it's reacting with the CO3 2 minus. Now remember, CO3 2 minus is a base because it's negative. Okay, so immediately you know that if those react, you're going to make H2O liquid and CO2 gas. It's immediate. That always happens when you have H and CO3 2 minus. What I'm going to be left over with here is the Na, which is plus 1. In this case, going with this NO3, which is minus 1. NaNO3. And I can balance this reaction by putting a 2 here and a 2 here. Now we're balanced. So let's look at what's happening in solution. Okay, so this is an aqueous solution, and there's two of them. So we have H plus NO3 minus, H plus NO3 minus. And this is reacting with this, two NAs, but it's aqueous. So Na plus, CO3 2 minus. Okay, and let's draw our big beaker to bring things together here. And what I'm looking for is my H with my CO3, and I know that's always going to make H2O and CO2, so I have my H2O liquid, circle it because it does not break up, and my CO2 gas, circle it because it does not break up, but the gas does bubble out, and I'm left with my NAs and my NO3s. Na plus, NO3 minus, NO3 minus. So in summary, there are two types of acid-base reactions. The first one is when you have something that can donate a hydrogen, okay, and something that has not just a minus, but a hydroxide minus, OH. In that case, you make just H2O. In the other case, you have something that can donate a proton, H+, and you have something that's a base, but it's not hydroxide, it's carbonate, CO3 2 minus. When that happens, we always make H2O liquid and bubble off some CO2. So, for your final multiple choice question, a pure white crystalline solid dissolves in water to yield a basic solution, okay, meaning it's a base. And when dissolved in water, it liberates a gas when excess acid is added to it. On the basis of this information, the solid could be A, potassium nitrate, B, potassium carbonate, C, potassium hydroxide, D, potassium bisulfate, and E, potassium chloride. Thanks.